Hello and welcome to the Sleepy Scientist. If you found your way here, you're probably seeking a peaceful way to unwind. What better way to relax than with a slow, soothing exploration of the chemistry that shapes our world, from the subtle beauty of atoms joining together in the dark, to the quiet bustle of molecules in motion. Tonight's journey invites you to discover the invisible forces behind everything you touch, taste, and tiptoe past. I'll keep things calm and steady, though I should warn you, science can be wonderfully fascinating. Hopefully this video won't be so interesting that it keeps you wide awake, but if it does, at least you'll drift off a bit wiser than before. Before we begin our gentle descent into the molecular realm, if you enjoy calm and curious content like this, I'd really appreciate it if you hit the like button and consider subscribing. Your support keeps this cozy corner of the internet alive and curious. And if you'd like, let me know where you're listening from and what time it is. I love seeing how far sleepy science can travel. Now, settle in, let your breathing slow, and allow today's thoughts to float away. Tonight, we'll explore why things react, combine, explode, or sometimes do nothing at all. We'll touch on a bit of body and brain chemistry too, but remember, nothing here is medical advice, just friendly, fact-check bedtime science. Picture holding something, anything, in your hand. Maybe a spoon, a feather, or half a cookie. Imagine cutting it in half again and again until you can't anymore. Eventually, you'd reach something so tiny it stops being that object and becomes something entirely different. An atom. Atoms are the basic building blocks of all matter. Everything around you, from pillows to toenails, mugs to screens, is made of atoms. Even you are a moving, talking, sometimes yawning cloud of organized particles. Atoms are incredibly small, but the science behind them is anything but boring. Let's start at the beginning. An atom is made of three main types of particles: protons, neutrons, and electrons. Think of atoms as tiny solar systems. Protons and neutrons cluster together in the center, forming the nucleus, and electrons whirl around in orbitals. But unlike planets orbiting a star, electrons behave more like fuzzy clouds. They exist in regions where they're likely to be, but we can never pinpoint their exact spot. They're the introverts of the atomic world, always just out of reach. The nucleus is dense and central, with protons carrying a positive charge and neutrons carrying no charge. Together, they make up the atom's heavy heart. The number of protons decides which element you have. 1 proton is hydrogen, 6 protons is carbon. Change the number of protons, and you have a different element altogether. Neutrons, while neutral, help hold the nucleus together, easing the tension among the positively charged protons, acting like peacekeepers at a very tiny summit. Electrons are the lively ones. They have a negative charge and exist in shells around the nucleus. The further from the nucleus, the more energy they hold. Electrons are like social butterflies, or maybe lightning bugs, constantly moving and occasionally leaping to new energy levels with a little nudge from heat or light. But here's a strange fact: atoms are almost entirely empty space. If the nucleus were the size of a pea, the nearest electron would be hundreds of feet away. So everything solid, including you, is made of particles floating in vast spaces. Matter feels solid because of the invisible forces between these particles, like standing in a room full of invisible walls. Atoms are astonishingly small, about 1/10,000,000,000th of a meter across. To put that in perspective, a single grain of sand has more atoms than all the stars in the observable universe. Yet, each atom follows the same fundamental rules of attraction, repulsion, bonding, and sometimes rebellion. When atoms join, they create molecules, which in turn make up everything: gases, liquids, solids, stars, and even you. But even a single atom alone has its own story. Take helium, just 2 protons, 2 neutrons, and 2 electrons. It's light, unreactive, and prefers to float solo. Oxygen, on the other hand, loves to bond and is essential for every breath you take. Imagine atoms at a party, helium quietly in the corner, oxygen and hydrogen dancing together to make water. Not all atoms are stable. Some are radioactive, their nuclei a bit too ambitious. They break apart over time, releasing energy, powering everything from smoke detectors to the Earth's core. Even instability has its place in the atomic story. What's amazing is how predictable all of this is. Thanks to centuries of science, we can map atoms, predict their behavior, and even use them to create new materials, medicines, and technologies. The periodic table is like a map of these atomic personalities. Some friendly, some solitary, some reactive, some calm. It's not just a scientific tool, but a chart of the universe's essential characters. Despite our knowledge, atoms remain marvelously mysterious, following the strange rules of quantum mechanics. where observing them can change what they do. It's science at its most poetic and puzzling. Atoms don't think or feel. They don't even know we're talking about them. But if they did, perhaps they'd be amused to know they're the stars of the show, shaping everything from thoughts to dreams to every breath you take. So here we are, in a world built from countless tiny somethings, mostly empty space, moving to ancient rules. And yet from that emptiness life and consciousness emerge. You emerge. And it all starts with the atom, the smallest something that makes up everything. Let's appreciate electrons for a moment, the tiny, nimble, unpredictable particles behind almost every chemical change you've ever seen or smelled. Electrons are much lighter than protons, but what they lack in size, they make up for in energy and spirit. They don't behave as you'd expect. If protons and neutrons are the reliable core, electrons are the creative, high-energy ones, always moving, always ready for something new. At their core, electrons carry a negative charge and are drawn to the positive pull of protons in the nucleus, not unlike a moth to a glowing light. This attraction keeps electrons close to the nucleus, but that doesn't mean they stay still. Electrons are always on the move, and their paths aren't neat or predictable as planets circling the sun. Instead, their behavior is best described by what's called a probability cloud. In classical physics, you can know exactly where something is and where it's headed, but electrons play by quantum rules where both location and speed are fuzzy concepts. Rather than tracing a clear path, scientists use a hazy cloud to show where you're likely to find an electron at any given moment. The denser the cloud, the higher the chance the electron is there. It's a bit like looking for a cat in a big house. You might not know its exact spot, but you have a good idea of its favorite cozy corners. These clouds, or orbitals, come in all sorts of shapes. Some are round, some look like dumbbells, and some are as strange as anything a sleep-deprived artist might dream up. Orbitals are grouped into layers called shells, which surround the nucleus. Each shell can hold a certain number of electrons, so the first holds up to 2, the second up to 8, the third up to 18, and so on. Electrons fill the lowest available energy levels first, a principle called the off-bar principle, and only move to higher shells when necessary or when they've absorbed energy. Now, this is where things get electrifying. An atom's chemical personality is mostly determined by its outermost electrons, called valence electrons. These electrons, sitting in the atom's highest energy shell, are most likely to interact with other atoms. If an atom's outer shell is full, it's stable and not very reactive, like someone already cozy under a blanket. But if the shell isn't complete, the atom will try to gain, lose, or share electrons, setting the stage for all kinds of chemical relationships. Take the noble gases like helium or neon, their outer shells are full, so they're content to keep to themselves, introverts of the periodic table. Sodium, on the other hand, has just one electron in its outer shell, itching to find a new home. Chlorine is missing just one electron to fill its outer shell and would gladly accept a spare. When sodium and chlorine meet, sodium hands over its extra electron, and together they form table salt, a chemical match made in heaven. This drive for stability, often called the octet rule, explains why atoms form the bonds they do. Atoms will share, donate, or take electrons to fill up their outer shells. Sometimes they share equally, as in covalent bonds. Other times, it's a one-way street, as with ionic bonds. Energy also plays a big part in electron behavior. When an atom absorbs energy, say, from heat or light, its electrons can get excited and jump to higher shells. But they don't stay there for long. They soon drop back down, releasing energy as light. This is how neon signs glow and why fireworks burst in color. When electrons in metals move freely, it gives metals their shine and ability to conduct electricity, like a communal cloud of electrons powering everything from toasters to trains. In chemistry, electrons are the ultimate matchmakers, mediators, and sometimes mischief makers. Their movements decide whether atoms will bond, how strong those bonds will be, and how easily they can be broken. Chemical reactions start when electrons are nudged from their usual spots and new compounds are created, but electrons also determine the physical properties of matter, how things look, feel, and behave, whether something is solid, liquid, or gas, acidic or basic, conductive or insulating, shiny or dull. It's all about what electrons are doing. Even the colors we see come from electrons. Pigments absorb certain wavelengths of light and reflect others, depending on how their electrons behave. A strawberry looks red because its electrons reflect red light. The blue sky, green leaves, and shimmering oil on water, all are products of electrons interacting with light in their own unique ways. Yet electrons still hold mysteries. Quantum mechanics, a science that describes their behavior, is so strange that even experts sometimes call it surreal. Electrons can act like both particles and waves. They can be in several places at once until observed. They can even tunnel through barriers. They're slippery, unpredictable, and absolutely vital to life. In the end, electrons might be tiny, but they're the restless hearts of atoms, always in motion, always shaping the world. From the bonds that hold molecules together to the sparks you feel touching a doorknob, electrons are at work. They are the quiet agitators, the energetic artists behind the scenes. We don't see them directly, but we experience their effects every moment. In our bodies, in our breath, even in our thoughts, which are electric signals carried by electrons darting through neurons. Small, elusive, essential. Without electrons, our world would be dark and dull. If atoms had personalities, their bonds would be their relationship statuses. Some cling tightly, some share generously, and some prefer a freewheeling communal life, as in metals. No matter the style, all bonds exist for one reason: stability. Atoms form connections not out of emotion, but from a logical need to reach a lower energy state. Let's start with the classic covalent bond. Two atoms sharing electrons equally, like kids sharing a snack. Each brings something to the table, and together both benefit. Covalent bonds are common among nonmetals, like hydrogen-oxygen forming water. This sharing gives water its special properties, from surface tension to its ability to dissolve so many things. But not all bonds are so polite. Sometimes, one atom wants an electron so badly, it simply takes it. This is ionic bonding. One atom donates, the other accepts, and both become charged ions. Opposite charges attract, pulling these ions together like magnets and forming a strong bond. Sodium and chlorine are a classic example of an unequal exchange in chemistry. Sodium has a single electron in its outer shell that it's eager to give away, while chlorine is just one electron short of a complete set and is keen to fill that gap. So, sodium happily hands over its electron to chlorine, like passing off a hot potato, while chlorine grabs it with relief. Once this transfer happens, sodium and chlorine become charged ions. Sodium becomes positive, chlorine negative. These ions are strongly attracted to each other and locked together to form sodium chloride, better known as table salt. In ionic bonding, there's no sharing or compromise. It's a straightforward transfer. The result is a strong attraction between the ions, which stack together in neat, geometric patterns, making salt crystals sparkle when you look closely. Then there's metallic bonding, which has its own unique style. Imagine a neighborhood potluck where everyone brings a dish and leaves it on the communal table, with no one remembering which dish was theirs. In metals, the outer electrons aren't tied to any one atom. Instead, they flow freely among all the atoms, creating a sea of electrons. This freedom is why metals conduct electricity so well. The electrons can move easily from place to place, forming an unbroken path for current. It's also why metals are shiny, and why you can shape them without them snapping apart. When you bend a wire or hammer a piece of metal, the atoms can slide past one another while staying bonded, cushioned by the roaming sea of electrons. You might wonder why atoms bother with all this bonding. The answer is simple: energy. Atoms are always trying to reach a state of lower energy, and bonding helps them get there. When atoms form bonds, energy is usually released. They become more stable, like finally sinking onto the couch after a long day. It's the drive for stability that encourages atoms to form connections with each other. The outermost, or valence, electrons are the key players in this process. Atoms are most reactive when their outer shells aren't complete. Hydrogen, with just one electron, is always looking for a partner to complete its shell, while fluorine, missing just one, is quick to pair up. These needs drive atoms to find each other and form bonds that satisfy both. Some bonds are incredibly strong. Diamonds, for example, are made of carbon atoms linked together in a rigid, three-dimensional network of covalent bonds, making them one of the hardest substances known. Other bonds are weaker, such as the attractions between water molecules, known as hydrogen bonds. These aren't full chemical bonds, but they're strong enough to hold water together, give it a high boiling point, and allow insects to walk across its surface. The strength of a bond depends on several factors, such as the types of atoms involved, their electronegativity, how strongly they pull on electrons, and how well they can hold onto shared or transferred electrons. Fluorine is the most electronegative element, eagerly pulling electrons closer in any bond. On the other hand, elements like cesium are more relaxed about electron custody. When bonds form, energy is usually released. This is called an exothermic reaction. When bonds break, energy is absorbed. An endothermic reaction. Lighting a fire is a good example. You have to put in energy to break the bonds in wood, but once broken, The new bonds that form release energy as heat and light. Chemical reactions often involve a mix of breaking and making bonds. Some reactions are slow, like rust forming on metal, while others are explosive, like fireworks, where bonds are broken and formed in a flash, releasing energy as heat, light, and sound. The world around you is held together by countless invisible bonds, each one a result of atoms seeking stability. Your own body is a living tapestry of this ongoing chemistry, proteins folding into specific shapes, DNA strands held together, and enzymes making reactions run faster. Even your thoughts depend on ionic exchanges inside your nerves. Bonds aren't just about structure, they're about function, life, memory, and change. Chemistry uses bonding to create order from chaos. Whether atoms share, take, or pool their electrons, it's always about reaching lower energy and greater stability, building something new. A gas becomes a liquid, a spark turns into a flame, all because atoms are constantly linking, rearranging, and letting go. It's poetic when you think about it. It's the same forces that hold salt together at work in stars, cells, and snowflakes. Every molecule, from sugar to gold, is shaped by the quiet partnerships of atoms, a silent, endless dance of holding hands and letting go. Energy is at the heart of every chemical reaction. It's the unseen currency passed between atoms as they form or break bonds, change shape, or transform completely. But even the most reactive chemicals often need a little push to get moving. This push is called activation energy, the minimum energy required to start a reaction. Without it, even the most promising ingredients would just sit quietly, like two people at a party waiting for someone to say hello. Take a box of matches. Inside are all the ingredients for fire, but nothing happens until you strike a match. That friction provides the activation energy needed to start the reaction. Heat is generated, molecules start vibrating, bonds stretch and snap, and new ones form. Combustion begins in a flash. Without that initial push, the match would just sit there, no matter how flammable. In their natural state, molecules are content to stay as they are. Activation energy is what nudges them to react. Imagine pushing a boulder up a hill. The boulder is your set of molecules. The hill is the energy barrier. Once you get the boulder over the top, it rolls down easily, just as a reaction takes off once it's started. Some reactions need very little activation energy, others need much more. That's why some chemicals are safe to store for years, while others react at the slightest touch. Once a reaction gets going, energy is either absorbed or released. That brings us to two types of reactions, endothermic and exothermic. Endothermic reactions absorb energy, like photosynthesis, where plants use sunlight to build sugars. Without constant sunlight, photosynthesis would stop. Another example is instant cold packs. When you mix water with ammonium nitrate inside, the reaction absorbs heat, and the pack turns cold. The chill you feel from a cold pack isn't because cold is being created, it's because heat is being drawn out of your skin as the reaction absorbs energy. On the other hand, exothermic reactions are the warm and generous type. They give off energy, typically as heat or light. Combustion is the most familiar example. When you light a candle, the wax's hydrocarbons react with oxygen, producing carbon dioxide, water vapor, and a satisfying amount of heat and flame. Fireworks, explosions, and even the way your body breaks down food all rely on exothermic reactions. Think of your cells as tiny, well-mannered combustion chambers. When you eat a banana, the sugars inside are gradually broken down in a series of controlled exothermic reactions. The energy released powers everything you do, from blinking your eyes to dreaming at night. Thankfully, these reactions are carefully managed by enzymes, so you don't burst into flames every time you eat a snack. Some reactions can go either way, depending on the situation. For example, when water evaporates, it absorbs heat, an endothermic process. But when water vapor condenses back into a liquid, it releases heat in an exothermic reaction. These reversals are part of an ongoing energetic dance, shifting as the environment changes. Interestingly, even dramatic reactions, like explosions, can involve only small changes in chemical bonds. It's the speed and scale of those changes that create the spectacle. A slow chemical reaction, like leaves decomposing, is just as real as the fast, fiery transformation of those same leaves in a blaze, just running on a different time scale. Catalysts can also change how reactions happen. These are substances that speed up a reaction by lowering the energy barrier, making it easier for reactants to reach the tipping point where the reaction starts. Catalysts aren't consumed in the process. They simply help things along, serving as behind-the-scenes matchmakers. In living things, enzymes are nature's catalysts, guiding almost every important reaction in your body. Without enzymes, your body's chemistry would be so slow you couldn't survive. For example, digesting bread would take years instead of minutes. Catalysts don't supply energy, they just make the path smoother and easier for molecules to rearrange. Understanding activation energy also helps explain why some substances are unstable. If a molecule is already in a high-energy state, it may need only a small nudge, like friction, heat, or even time, to fall apart or transform. That's why explosives are stored carefully, and why medicines or chemicals are often kept cool and away from sunlight. By reducing the available energy in the environment, you make it harder for unwanted reactions to start. In the end, chemical reactions are nature's way of helping atoms find a more comfortable, lower energy arrangement, like fluffing your pillow until it's just right. Some atoms settle in easily, while others need a little warming up. Sometimes, all it takes is a spark to get things moving. Whether you're feeling the warmth of a hand warmer, the chill of a cold pack, or watching the soft light of a candle, you're experiencing energy at play on the atomic level. There's always a reason for every transformation, and nearly always, it comes down to just the right amount of energy arriving at the perfect moment. It's easy to overlook these changes. We light a match, cook a meal, or watch the sun stream through a window without thinking about the atomic ballet taking place. But behind every flame, every breeze, every breath, there's a reaction, sparked, balanced, and guided by the rules of energy. And often all it takes to begin is a small push. Now, let's talk about acids and bases, the mood makers of chemistry. When they enter the scene, things can get lively. Acids and bases can make metals fizz, change the color of solutions, or turn simple ingredients into kitchen experiments. While we think of them as opposites, they're really two sides of the same coin, defined by how they interact with water and two important ions, hydrogen ions OH there and hydroxide ions OH. To understand acids and bases, let's start with water. Water seems calm and neutral, but at any moment, some water molecules are splitting into H and OH ions, then recombining back into water. It's a constant, quiet give and take. An acid is any substance that increases the concentration of hydrogen ions when added to water, a generous donor giving out H ions. A base, in contrast, either removes those hydrogen ions or adds hydroxide ions, tipping the balance in the other direction. Acids push the balance towards more H, while bases pull it towards more OH. This balance is measured by the pH scale, which runs from 0 to 14. Pure water at a pH of 7 is neutral. Anything below 7 is acidic, above 7 is basic or alkaline. The pH scale is logarithmic, meaning each step represents a tenfold change. So, a solution with a pH of 4 is 10 times more acidic than one at pH 5. Lemon juice with a pH around 2 is quite acidic. Vinegar sits around pH 3. Baking soda is mildly basic at about pH 9, and bleach can be very alkaline, reaching up to pH 12 or 13. At the extremes, both acids and bases can be corrosive and reactive. What makes acids so reactive is their willingness to give up hydrogen ions. These tiny, positively charged particles can interact with molecules in powerful ways, speeding up reactions, altering structures, or even causing burns. Bases, meanwhile, mop up those hydrogen ions or add hydroxide ions to neutralize them. The tug-of-war between acids and bases over H ions is at the heart of countless reactions. Acids and bases are everywhere. Your stomach uses hydrochloric acid to digest food and kill germs, while your pancreas counters with bicarbonate, a mild base, to neutralize the acid as food moves onward. It's a careful balancing act, strong enough to digest, but not so strong that it harms you. In the kitchen, acids add brightness and flavor. Think lemon juice on salad or vinegar in marinades. They help tenderize meat and turn milk into cheese. Bases are less common in cooking, but they're important too. Baking soda, a mild base, produces bubbles of carbon dioxide when it reacts with an acid, making cakes and bread rise. One of the most satisfying moments in acid-base chemistry is neutralization. When an acid and a base are mixed in the right amounts, they react to form water and a salt. Not always table salt, but any ionic compound made from the acid's negative ion and the base's positive ion. This can happen quietly or with a fizz, as in the classic vinegar and baking soda reaction, which produces carbon dioxide bubbles, water, and a harmless salt. That classic science fair volcano is more than just harmless fun. It's also a beautiful example of chemistry in action, a peaceful handshake between opposites. But when strong acids and strong bases meet, things can get much more intense, sometimes releasing heat or even producing dangerous substances. For example, bleach is highly basic, and if you add vinegar and acid, the reaction can release toxic chlorine gas. Definitely not something to try at home. In chemistry, opposites can attract. But their interactions aren't always friendly. Acids and bases do much more than just create bubbles or change colors. They can alter the structure of molecules, affect chemical pathways, or act as catalysts or inhibitors. For living things, this sensitivity to pH is essential. Enzymes, the proteins that speed up your body's reactions, are especially sensitive to pH. If the environment gets too acidic or too basic, enzymes can lose their shape and stop working, a process called denaturation. That's why your body keeps your blood pH tightly controlled, right around 7.4. Even a small shift can have serious consequences. Some organisms, though, have adapted to extreme H conditions. Acidophiles are microbes that thrive in very acidic places like volcanic springs, while alkalophiles live in basic environments such as soda lakes. Their biochemistry is specially tuned for conditions that would destroy most other life forms. This reminds us that chemistry is happening everywhere, not just in tidy laboratory glassware, but out in the world, even at the edges of what life can tolerate. pH also plays a huge role in the environment. Acid rain, caused by pollution, can lower the pH of lakes and soils, harming plants and aquatic life. Similarly, rising levels of carbon dioxide are making the oceans more acidic, a process called ocean acidification, which affects marine animals' ability to build shells and regulate their internal chemistry. Even small changes in pH can have big effects on delicate ecosystems. Acid-base chemistry is also at the heart of many industries. Wastewater treatment, battery technology, dyeing fabric, and cleaning all rely on the balance between acids and bases. Lead-acid car batteries, for instance, use sulfuric acid to generate electricity. In cleaning products, bases help dissolve grease and dirt. It's not magic, just hydrogen and hydroxide ions doing their work. Indicators are another delightful aspect of acid-base chemistry. These are substances that change color depending on the pH. Litmus paper turns red in acid and blue in base. Phenolphthalein, a classroom favorite, is colorless in acid but bright pink in base. Even red cabbage juice works as a natural pH indicator, shifting through a rainbow of colors as the solution changes from acidic to basic. These colorful changes aren't just fun. They're a vivid reminder of the dynamic world of acids and bases. But beneath the fizz and color is a deep, elegant system that drives countless processes in our bodies, our environment, and our technology. At its core, acid-base chemistry is about balance, the give and take, the push and pull, finding just the right mix. Whether it's using vinegar to sour the wasp sting, taking an antacid for a sour stomach, or scrubbing a stain with bleach, the story is always about ions interacting, electrons shifting, and molecules rearranging themselves into something new. Acids and bases might seem like opposites, but they're actually partners in a delicate negotiation. One offers, the other accepts, and in the right proportions, they reach a calm, neutral balance. Until, of course, someone adds more lemon juice to the salad. Now, let's talk about temperature and pressure, the master manipulators of the molecular world. While they might seem like things you control with a thermostat or air pump, in chemistry, they set the stage for reactions, coaxing particles to move, collide, and interact, sometimes slowly, sometimes explosively. This brings us to the kinetic molecular theory. At its heart, it says that all matter is made of constantly moving particles. Even in what seems like a perfectly still block of ice or wood, atoms and molecules are vibrating and jiggling. The more heat, the faster they move; the less heat, the slower the motion. Imagine a room of people. If everyone is calm and strolling, collisions are rare. But if you turn up the energy, maybe with music or caffeine, everyone starts moving faster, bumping into each other more often. The same is true for molecules. Heat is energy, and when you add heat, particles move faster, collide more often, and with more force. Chemical reactions happen when molecules collide just right, with enough energy to break old bonds and create new ones. Heating a system increases both the frequency and energy of these collisions, making reactions more likely. That's why cookies bake faster in a hot oven. Food spoils more quickly in warm weather, and your metabolism speeds up with a fever. But not every collision leads to a reaction. Molecules need just the right amount of energy and the proper orientation, like tossing puzzle pieces together and only getting a fit if they collide correctly. Extra heat helps more of those pieces snap together successfully. Pressure also plays a big role, especially in gases. Increasing the pressure squeezes molecules closer together, making collisions more frequent. Imagine a crowded club versus an open fielding. More close encounters mean more chances for reactions. Temperature and pressure can also influence which reactions occur and what products are formed. Some reactions only happen at high heat or under high pressure. Others can reverse direction if you change these conditions. This is vital in industrial chemistry, where optimizing heat and pressure can dramatically improve efficiency. The Haber process, for example, creates ammonia for fertilizer by combining nitrogen and hydrogen under high temperature and pressure, a reaction critical to global food production. Temperature affects the reaction rate constant, described by the Arrhenius equation, which shows that even small temperature changes can have a big effect on how fast reactions proceed. Higher temperatures mean more molecules have enough energy to get over the activation energy barrier, but heat doesn't just make things go faster. It can also change substances themselves. Solids melt, liquids evaporate, gases condense, all driven by the amount of energy available. Melting ice or boiling water are physical changes, not chemical ones, but they show how powerful heat can be at disrupting structure. A few reactions actually slow down when heated. Chemistry, usually when high temperatures make the products unstable or shift the reaction's balance. But those are the exceptions to the general ruling in chemistry. Temperature and pressure are powerful levers, shaping the behavior of matter at every scale. That's why, in sensitive biological systems, there's usually a just right zone. It's too cold, everything slows down. If it's too hot, delicate molecules can begin to unravel. Pressure has its own quirks too. While it most strongly affects gases, it can influence reactions involving solids and liquids, especially when the reaction changes the number of particles in the system. If fewer gas molecules are produced than you started with, increasing the pressure can encourage the reaction to move forward. If more gas molecules are made, raising the pressure can actually slow things down. It's all about shifting the balance to reduce crowding. You see the interplay of heat and pressure in everyday life. Cooking is a great example. Pressure cookers trap steam, raising both the internal pressure and the boiling point of water, which lets food cook faster and stay moist. Tough beans and meat soften quickly because of simple physics and chemistry at work. Deep in the ocean, extreme pressures change how gases behave, affect solubility, and alter the course of chemical reactions. Microbes living near hydrothermal vents thrive in these extreme environments, using heat and pressure to power unique biochemistry. Life, it seems, is endlessly adaptable when it comes to the rules of thermodynamics. Chemists in the lab use temperature and pressure with precision. Some reactions that would take days at room temperature can finish in minutes with a little heat. Sealed, pressurized vessels called autoclaves allow reactions that wouldn't happen in open air. In pharmaceutical manufacturing, chemistry-controlled temperatures ensure the complex molecules form just right, with the proper structure and purity. But it's a delicate balance. Too much heat and sensitive compounds fall apart. Too much pressure and you risk containment problems. Sometimes it's not about speed, but about control, letting reactions proceed slowly and predictably to avoid unwanted side products or even explosions. What's amazing is how universal these principles really are. Whether you're baking bread, studying volcanoes, designing rocket fuel, or fermenting gourd, the same basic chemistry applies. Heat gives motion, pressure brings particles closer, and together they shape reactions in subtle and dramatic ways. Even the weather follows these rules. Clouds form as warm, moist air cools and condenses. Lightning flashes when charge separates in stormy clouds, and thunder is simply the sound of air being heated so quickly that it expands faster than the speed of sound. Chemistry, physics, and atmosphere all collide to create the world's drama. Most of what we see around us is shaped by invisible forces acting on tiny particles. Molecules don't decide to react. They're moved by energy, motion, and proximity. Heat gives speed, pressure gives the squeeze, and together they unlock transformation, one collision at a time. From the stillness of an ice cube to the shimmer of steam, from the enormous pressure of the deep sea to the gentle hum of a kettle, the dance of particles is always ongoing, colliding, rearranging, responding to their environment. And at the heart of it all is a simple truthing: nothing reacts without a little motivation. And temperature and pressure are excellent motivators. In textbooks, chemical reactions can look like simple one-way streets: mix reactants, get products, and you're done. But in reality, chemistry is rarely that final. Many reactions are reversible. Molecules can combine, split apart, and sometimes swing back and forth endlessly. This is the world of reversible reactions, where the finish line is more like a roundabout than a dead end. A reversible reaction is just what it sounds like, a process that can go in both directions. Reactants become products, but those products can also break down into reactants. Instead of one side winning, the system settles into a state of balance, where both directions keep happening at the same time and in just the right proportions. This balance is called equilibrium. Equilibrium doesn't mean nothing is happening. In fact, dive into the chemistry. At equilibrium, the reaction is still going. Molecules are forming and breaking apart, but they're doing so at equal rates. It's like watching people get on and off an escalator at the same pace. The crowd at the top and bottom stays constant, even though the movement never stops. Chemical equilibrium is central to many natural and industrial processes. It explains why some reactions never seem to finish, why others stall halfway, and why changing conditions can tip the balance. At its core is always seeking a balance between competing forces. Imagine a simple reversible reaction: hydrogen and iodine, both colorless gases, combine to form purple hydrogen iodide gas. As the reaction proceeds, more and more hydrogen iodide is formed, but eventually, some of it starts to break back down into hydrogen and iodine. Eventually, the rate of formation matches the rate of decomposition, and you're left with a steady mixture of all three gases. This equilibrium is sensitive to temperature, pressure, concentration, and even catalysts. Here's where a bit of chemical wisdom comes in. Thanks to the 19th centuryist Henry Lee Chatelier, he noticed that when you disturb a system at equilibrium, the system responds to counteract the change. This is known as Lee Chatelier's principle. Think of a room with a thermostat set to keep things cozy. If someone opens a window and cold air rushes in, the heater kicks on to restore the temperature. Chemistry behaves similarly: add more reactant, and the system shifts to use it up, remove product, and it works to replace it, add heat, and the system adjusts, often by favoring the endothermic direction. Take the equilibrium between nitrogen dioxide brown gas and nitrogen tetroxide colorless. At equilibrium, the mixture looks faintly brown. Cool it down, the brown fades and more colorless gas forms, absorbing heat. Warm it up, the brown deepens as more nitrogen dioxide appears. The system always tries to undo whatever change you introduce. Pressure works the same way, especially with gases. Squeeze the gases into a smaller volume, and the system shifts toward the side with fewer gas molecules to relieve the pressure. If a reaction produces more gas, increased pressure pushes the balance in the opposite direction. Even changing the concentration of one component can tip the equilibrium. Add more of one, and the reaction uses it up, takes some away, and the reaction replaces it. This constant adjustment is how chemistry maintains balance, gracefully and persistently. Equilibrium is vital in biology. Our bodies depend on countless reversible reactions that must be finely tuned. For example, in your lungs, high oxygen levels favor oxygen binding to hemoglobin. In your tissues, where oxygen is low, the equilibrium shifts and oxygen is released. Another example is the carbonic acid equilibrium in your blood, where carbon dioxide dissolves in water to form carbonic acid, which then breaks down into bicarbonate and hydrogen ions. This reversible reaction is vital for keeping your blood pH within a narrow, healthy range. If carbon dioxide levels rise, more acid forms and the pH drops. If sulfur falls, the reaction shifts the other way. Your body carefully manages this process, using the lungs and kidneys in tandem to maintain chemical balance. In industry, understanding and controlling equilibrium is equally important. Take the Haber process, where nitrogen and hydrogen gases react to form ammonia, a key ingredient in fertilizers. By fine-tuning temperature, pressure, and concentrations, chemists can nudge the equilibrium toward producing more ammonia. It's a constant balancing act between chemical principles and practical efficiency. It's important to note equilibrium doesn't mean equal amounts of reactants and products. Instead, it means the forward and reverse reactions are happening at the same rate. Sometimes the mixture is mostly products, other times mostly reactants. The proportions depend on the energy landscape, which arrangement is more stable, and how much energy is needed for the reaction to go back and forth. There's something poetic about equilibrium. Nature doesn't like extremes, it prefers moderation, feedback, and compromise. The world isn't full of one-way reactions. Rather, it's teeming with reversibility, with systems that shift, respond, and settle into a state where everything appears calm, even though constant movement is happening underneath. Equilibrium is a dynamic pause, a moment when change balances itself out. It's like a tug of war where neither side is winning, but both are pulling equally. Peace through motion, not stillness. Understanding equilibrium gives you a new perspective on the world. You start to see balance everywhere, in chemical reactions, in nature, even in social dynamics. Systems respond to changes, resist disruptions, and find new steady states. Chemistry is simply very good at demonstrating this principle. So next time you hear about something being on balance, or notice steam condensing on a window, or even just take a deep breath, Remember, equilibrium isn't the end of change, but the start of a subtle, continuous negotiation. Molecules are always moving, always adjusting, and always striving for fairness. Now, let's look at chemistry's most dramatic moments: explosions. Explosions are intense displays of rapid energy release, usually through chemical reactions. At their core, explosions are about releasing a lot of energy very quickly, resulting in heat-like gases and powerful shock waves. Sometimes this energy comes from a chemical reaction, other times it's from a sudden physical process or even a nuclear event. The common thread is speed reactions happening in milliseconds, unleashing enormous energy at once. Most chemical explosions are a type of combustion, rapid reactions with oxygen that produce heat and light. Combustion isn't always explosive. A candle flame, for instance, is a gentle, controlled burn. But change the conditions, add more fuel, more oxygen, or confine it, and that same chemistry can become explosive. Take a hydrogen balloon on its own, harmless. Add a spark and hydrogen reacts instantly with oxygen to form water vapor, releasing a huge burst of energy. The air expands almost instantly, creating a shockwave and a bang. The key to most explosions is rapid oxidation. Oxidation is when molecules lose electrons, often to oxygen. This transfer breaks chemical bonds and forms new, more stable ones, releasing energy in the process. In a slow burn, this energy is released gradually. In an explosion, it's unleashed all at once, like a spring suddenly uncoiling. Fireworks are a wonderful example of controlled explosions. Each firework contains oxidizers, fuels, and color, producing compounds. When ignited, the oxidizer helps the fuel burn rapidly, generating hot gases that launch the firework skyward. As it bursts, different metal salts create beautiful colors: strontium for red, barium for green, copper for blue, and sodium for yellow. A dazzling chemistry show. TNT, trinitrotoluene, is a famous example of an explosive where both fuel and oxidizer are built into the same molecule. When detonated, TNT's atoms rearrange rapidly, producing hot gases and releasing a huge amount of heat. Because this energy is released faster than the surroundings can absorb, you get an explosion. Interestingly, TNT is quite stable under normal conditions. You can handle it safely. It needs a detonator, a smaller, more sensitive explosive, to provide the initial energy to get things started. Once triggered, the reaction races through the material, turning solid explosive into a storm of hot gas and pressure in an instant. Explosions can be categorized by how quickly the reaction moves through the material. In a deflagration, the reaction moves at subsonic speeds, like in gunpowder. In a detonation, it moves faster than sound, creating a shockwave, the difference between a firecracker and a high-powered explosive. Explosions aren't always intentional. Sometimes they're accidents, unexpected reactions triggered by the wrong conditions. Some of the most common accidental explosions actually happen in the kitchen. Take flour, for example. By itself, it seems harmless, but suspend fine flour dust in air, add a spark, and you get a dust explosion. The tiny particles have a large surface area and react with oxygen quickly. In a confined space, a single spark can ignite the whole cloud in an instant. That's why flour mills use explosion-proof equipment, and why it's wise to keep your kitchen tidy when baking. Aerosol cans are another example. They contain flammable propellants under pressure. If overheated, the pressure inside builds until the can bursts near a flame or spark. The results can be explosive. Even oil in a hot pan can become dangerous. If it overheats and catches fire, pouring water on it causes the water to instantly vaporize, hurling burning oil everywhere in a dramatic fireball. Even simple reactions like baking soda and vinegar can be enthusiastic. When these mix, carbon dioxide gas is produced rapidly, causing bubbling and fizzing. Not explosive, but it's a gentle reminder of how reactive everyday substances can be. In other settings, explosive reactions are carefully harnessed for practical purposes. Car airbags, for example, deploy using a controlled explosion. Sodium azide inside the airbag rapidly breaks down into nitrogen gas, inflating the airbag in a fraction of a second. In mining and construction, explosives like dynamite or NFOs, ammonium nitrate, and fuel oil are used to move rock and earth. These materials are designed to be stable until activated, then release tremendous energy when triggered. The power of explosions comes not just from what's inside the material, but from how the reaction spreads. A chain reaction of molecular changes rippling through the substance. Even the natural world puts explosive chemistry to use. Volcanoes are some of Earth's most dramatic chemists, blending heat, pressure, and reactive gases to create eruptions. Deep beneath the surface, molten rock mixes with water and gases like carbon dioxide and sulfur dioxide. When pressure builds high enough, the mixture bursts forth, releasing heat, ash, and gas in a spectacular show, it's a reminder that the Earth is always reacting, bubbling, and occasionally erupting. On a much smaller scale, even living cells can stage tiny chemical explosions. Take the bombardier beetle, for example. To defend itself, it sprays a boiling chemical jet from its abdomen. How? It stores two reactive substances, hydrogen peroxide and hydroquinone, in separate compartments. When danger strikes, it mixes them in a reaction chamber, where enzymes trigger a violent reaction that produces heat and pressure. The resulting burst of gas propels a scalding spray at any would-be predator, a reminder that nature, too, has mastered the art of chemical reactions. Explosions themselves aren't bad. They're simply fast reactions doing what reactions do, breaking old bonds, making new ones, and releasing energy. The real trick is managing them. If the reaction's too slow, it fizzles. Too fast, and it can be destructive. Chemists, engineers, and even cooks have learned to walk this fine line, harnessing explosive chemistry to power engines, launch rockets, save lives, and create dazzling displays. It's easy to think of explosions as rare, wild outliers, extreme events at the edge of chemistry. In truth, they're just reactions sped up. The same principles apply whether you're lighting a candle or igniting rocket fuel. It's about energy, molecules, and the rate at which change happens. So next time you see fireworks blooming across the sky, or hear kernels popping into popcorn, you're witnessing atoms rearranging in a rush of heat, sound, and expansion, chemistry unleashed, not chaotic, just fast and sometimes gloriously loud. Now, let's turn the spotlight to carbon, the true superstar of chemistry's red carpet. Carbon's not the flashiest, heaviest, or rarest element, but when it comes to versatility, structure, and transformation, it's unmatched. Carbon is the molecular shapeshifter, building everything from butterflies and bananas to your DNA and the graphite in your pencil. If chemistry had celebrities, carbon would arrive in a limousine made of itself. What sets carbon apart is its bonding ability. Unlike most elements, carbon can form up to 4 bonds at once, a magic number in the atomic world. This gives it the flexibility to create stable, complex structures, long chains, rings, branches, double and triple bonds. Carbon's talent for catenation, bonding to itself, lies at the heart of its versatility. No other element comes close. Even silicon, which tries to mimic carbon, is only a pale imitation. Organic chemistry, the study of carbon-based compounds, revolves around this remarkable ability. Carbon atoms can connect with each other and with other elements in endless combinations. The frameworks of organic molecules are carbon scaffolds, dressed up with functional groups, small clusters of atoms that give each molecule its unique character. Like costumes, these groups define how the molecule behaves. Add an OH and you get an alcohol, swap in SOH and it's a carboxylic acid, add NHL and it becomes an amine. Underneath, it's all carbon, simply playing different roles. Carbon doesn't just form molecules, it builds architecture. The simplest are straight chains, but those chains can branch, bend, or loop into rings. Cyclohexane, for instance, is a 6-carbon ring that looks like a tiny hexagonal playground. Aromatic rings like benzene feature electrons that float in a shared cloud, making them unusually stable and chemically interesting. Some organic molecules are gigantic, like proteins, long chains of amino acids folded into specific shapes, or DNA, a double helix stretching for billions of atoms. Others, like methane, are tiny, just 1 carbon bonded to 4 hydrogens. But whether big or small, the rules are the same. Carbon in the center, bonds radiating out, holding everything together like a molecular socialite with unmatched networking skills. Carbon's 4 arms also let it form double and triple bonds. Double bonds share 2 pairs of electrons, making a stronger, shorter bond than a single one. Triple bonds are even stronger and shorter. These bonds change a molecule's shape and reactivity, giving organic chemistry its richness and complexity. And then there are isomers, molecules with the same formula but different structures. Carbon loves isomers. With the same set of atoms, it can build a variety of structures, each with different properties. For example, butane and isobutane both have the formula CH2, but their arrangements are different, leading to distinct boiling points and behaviors. It's like rearranging furniture. The pieces are the same, but the room feels entirely different. Stereochemistry adds another twist. Some molecules are mirror images of each other, like left and right hands. These are called enantiomers, and in biology, one form can heal while the other may do nothing or even harm. Carbon's 3-dimensional bonding lets it create these subtle differences, making life's chemistry both precise and fascinating. Organic chemistry is sometimes called the chemistry of life and of confusion. The molecules are many, the names are long, and the rules full of exceptions. But within this complexity is beautiful order, a system built on a tiny atom with big ambitions. Life as we know it is essentially a grand carbon experiment. Proteins, lipids, carbohydrates, nucleic acids, the four great classes of biological macromolecules, are all carbon-based. Enzymes which catalyze your body's reactions are proteins folded into elaborate shapes, each custom-built for a task. Cell membranes are made from lipids, forming flexible self-sealing barriers. Carbohydrates provide energy and structure. DNA, the blueprint of life, is a winding ladder of carbon, hydrogen, oxygen, nitrogen, and phosphorus. All these functions, energy storage, information transfer, structural support, depend on carbon's knack for making stable yet dynamic bonds. These bonds are strong enough to hold things together, but not so strong that molecules can't adapt or change. Life needs this balance, a scaffold that allows for complexity and motion. Even life's origins likely began with carbon chemistry. Scientists simulating early Earth conditions have created simple carbon compounds, amino acids, for example, using basic ingredients and a spark of energy. These experiments suggest that, given time and the right mix, carbon can build extraordinary things. And carbon's reach goes far beyond biology. In materials science, carbon forms everything from synthetic polymers to cutting-edge nanomaterials. Plastics, for better or worse, are organic compounds, long chains of repeating carbon units. Carbon nanotubes and graphene are at the cutting edge of materials science, pushing the boundaries of strength and conductivity. These remarkable forms of carbon are opening doors to new technologies, from flexible electronics to the ambitious dream of space elevators. Even the fuels we use every day, like gasoline and natural gas, are hydrocarbons, chains of carbon with hydrogen sidekicks, packed with stored energy just waiting to be released. Carbon's versatility is also shown in its pure forms. As graphite, carbon is soft and slippery, ideal for pencils and lubricants. As diamond, it's hard and dazzling, with each atom locked into a strong three-dimensional network. The difference between graphite and diamond isn't the atoms themselves, but how those atoms are arranged. Same element, completely different personalities, and of course carbon is central to climate chemistry. Carbon dioxide, a simple molecule of one carbon and two oxygens, is a vital greenhouse gas. In small amounts, it's essential, but in excess, it's a major concern for global warming and sustainability. Its ability to trap heat has made it the centerpiece of conversations about our planet's future. Carbon, then, isn't just the stuff of life, it's the stuff of consequence. Despite its importance, carbon is rarely flashy. It's often black or colorless, only sparkling when squeezed into diamond. But in the world of atoms, carbon is a quiet genius. It builds molecules of life, materials of modern society, and the cycles of nature. It bends, bonds, loops, and links in ways other elements can only dream of. If chemistry were a stage production, carbon would be the playwright, director, lead actor, and set designer, always central, rarely demanding the spotlight, unless something goes wonderfully right or terribly wrong. It's the reason you're made of molecules and not moon rocks. It's why your cells work, your food digests, and your thoughts even happen. All of that, every heartbeat and breath, comes down to one element: four bonding arms, a passion for structure, and an endless drive to connect. Carbon isn't just chemistry's diva, it's the storyteller of life. Now, let's talk about a process that sounds futuristic but is fundamental: redox. It might sound like a sci-fi robot, but redox is short for reduction oxidation, and it's one of the universe's most important chemical processes. Redox reactions are all about the exchange of electrons, the tiny energetic particles that make atoms tick. Anywhere you find burning, rusting, charging, or digesting, you can bet redox chemistry is at work behind the scenes. At its heart, a redox reaction is like a coordinated game of electron musical chairs. One substance loses electrons, that's oxidation, and another gains them, that's reduction. These two processes are forever linked. When one atom gives up an electron, another must take it. It's a constant give and take, a relay of electrons. Here are the basic definitions: oxidation, loss of electrons; reduction, gain of electrons. This might sound backwards since reduction seems like it should mean losing something, but in chemistry, gaining negatively charged electrons makes the overall charge more negative, or reduced. A handy way to remember is the acronym OLRIG. Oxidation is loss, reduction is gains of electrons. Electrons are the energetic currency of atoms. During a redox reaction, they're passed around like hot potatoes. Some atoms, like oxygen, are natural electron hoarders and love to pull electrons towards themselves. hence their starring role in oxidation reactions. Others, like the alkali metals, are generous and eager to give up electrons to achieve stability. Take the classic example, rusting iron. When iron is exposed to water and oxygen, it slowly transforms into iron oxide rust. Here's what's happening: iron atoms lose electrons, they're oxidized, and those electrons are picked up by oxygen in the presence of waters, reducing the oxygen atoms. The result is iron oxide, a chemically stable but structurally weak compound. Rust is a visible sign of electrons trading hands and the underlying metal changing over time. Other redox reactions are more dramatic. Combustion, for example, is oxidation on fast forward. Burning wood, gasoline, or even a marshmallow involves carbon and hydrogen losing electrons to oxygen, releasing energy as heat and light. The rapid transfer of electrons breaks and makes bonds in a rush, giving us flames and warmth, chaotic, beautiful, and pure redox. Redox isn't just about things falling apart, it's also how your body releases energy. Inside your cells, a process called cellular respiration breaks down glucose, stripping electrons and passing them through a series of proteins in your mitochondria. This controlled flow of electrons powers the production of ATP, your body's energy currency. Oxygen is the final electron acceptor in this chain, which is why you need to breathe. Without it, the whole process grinds to a halt. This flow of electrons is strikingly similar to what happens inside a battery. Batteries are portable redox reactions. The anode gives up electrons oxidized, the cathode accepts them reduced. Connect the battery in a circuit, and electrons flow from anode to cathode, powering your devices. Inside, ions move through an electrolyte to balance the charge. In an alkaline battery, zinc is the anode and gets oxidized, while manganese dioxide is the cathode and is reduced. The arrangement allows for a steady, controlled flow of electrons, reliable redox at work. Rechargeable batteries, like lithium-ion types, use reversible redox reactions. When you charge them, electrons are pushed back through the system, restoring the original chemical states, like rewinding a movie to watch again. Balancing these reactions is the art and science of battery design. Redox reactions also power photosynthesis, the process plants use to turn sunlight into sugar. In a green leaf, light splits water, pulling electrons away from hydrogen and passing them through an electron transport chain. The electrons eventually help convert carbon dioxide into glucose, storing the sun's energy in chemical bonds. It's the reverse of cellular respiration. Instead of burning sugar to release energy, the plant is using energy to build sugar. In the lab, redox reactions are used for electroplating, coating an object with a thin metal layer by passing a current through a solution. This can protect surfaces or just make them shiny. Your silverware, jewelry, and car's chrome parts might all owe their finish to redox chemistry. Redox is even used to monitor health. Blood glucose meters use tiny redox reactions to detect sugar levels. Breathalyzers detect alcohol by oxidation. Water treatment systems use redox reactions to remove contaminants, either by oxidizing them into safer forms or reducing them so they can be filtered out. A fascinating aspect of redox is how it involves electron affinity, how strongly an atom wants to gain electrons and ionization energies, how much energy it takes to remove one. These properties decide who wins. The chemical game of musical chairs. Fluorine, for instance, is the ultimate electron hog, eager to grab electrons from anything, making it extremely reactive. By contrast, alkali metals like sodium are happy to give up electrons, making them excellent at reducing other substances. In redox chemistry, the roles of each participant are formalized. The substance that loses electrons is called the reducing agent, because by giving up electrons, it reduces the other substance. The one that gains electrons is the oxidizing agent, because by accepting electrons, it oxidizes the other. It's a kind of odd generosity. By giving something away, you cause reduction, and by taking, you cause oxidation. Redox is deeply relational chemistry. Nothing happens in isolation. What makes redox reactions so fascinating is just how widespread they are. They power life, industry, nature, and even the electronics in your pocket. Redox can be slow, like rust creeping across an old fence, or fast, like a spark igniting a gas stove. They can be helpful, like extracting energy from food, or harmful, like corrosion eating away at a bridge. But every redox reaction boils down to electrons finding new homes. Each one tells a story of change, atoms adjusting to a new balance, electrons moving to a more stable neighborhood, and systems shifting toward lower energy. It's chemistry at its most dynamic and interconnected, and, like any good exchange, it only works when both sides play their part. Whether in a leaf, a lung, or a lithium battery, electrons are always moving, quietly driving the world forward. In chemistry's grand theatre, the spotlight usually falls on the big players' atoms reacting, bonds breaking, energy flying around like confetti. But behind the curtain are the unsung heroes making it all happen faster, smoother, and with less fuss: catalysts, the quiet helpers of the molecular world. They never take center stage. They don't get used up or changed themselves. But without them, many reactions would crawl along so slowly you'd still be waiting for your cookies to bake next week. A catalyst is a substance that speeds up a chemical reaction without being consumed. It's like a molecular matchmaker, helping reactants find each other and encouraging them to get on with it. When the reaction is finished, the catalyst steps aside, unchanged and ready for another round. It's the ultimate facilitator, efficient, discreet, and indispensable. Imagine two molecules want to react, but the path is blocked by a high-energy barrier, the dreaded activation energy. Maybe their collisions aren't quite right, maybe their bonds are just too strong. Enter the catalyst. It offers a shortcut, an alternate route with a lower energy barrier. The result? The reaction happens more quickly and with less energy, often without needing higher temperature or pressure. It's like taking a secret side street to skip a traffic jam. Same destination, less hassle. Catalysts come in many forms. In industry, metals like platinum and nickel catalyze processes from fuel production to hydrogenation. In cars, catalytic converters help turn toxic exhaust gases into less harmful substances before they leave the tailpipe. But the most elegant and astonishing catalysts are inside you: enzymes. Enzymes are biological catalysts made of proteins, and they are astonishingly good at their jobs. They can speed up reactions by millions or even trillions of times, turning slow chemical steps into lightning-fast transformations. Without enzymes, life would grind to a halt. Digestion, cell repair, energy production, immune responses all depend on enzymes working constantly to keep you alive. Each enzyme is highly specific. It usually works with just one kind of molecule. It's its substrate and catalyzes one type of reaction. The enzyme's structure includes an active site, a specially shaped pocket that fits the substrate perfectly. When the substrate binds, the enzyme holds it in just the right position to help break or form bonds efficiently. Sometimes the enzyme torques the molecule, making its bonds easier to rearrange. Other times, it brings two molecules together, nudging them into perfect alignment. When the reaction is done, the products drift away and the enzyme resets, ready for the next round, a molecular assembly line where the workers never get tired. A classic example is the enzyme catalase, found in nearly all living cells. Its job is to break down hydrogen peroxide, a potentially harmful byproduct of metabolism, into harmless water and oxygen. One molecule of catalase can convert millions of hydrogen peroxide molecules each second. You can even see it in action. Add hydrogen peroxide to fresh potato or liver, and you'll see bubbles of oxygen released. That's catalase protecting cells from oxidative stress. Another star is amylase, which begins breaking down starches in your saliva as soon as you start chewing. That's why bread or crackers taste a bit sweet if you hold them in your mouth. The long chains of starch are being chopped into sugars by enzymes right there on your tongue. Enzymes are sensitive to their surroundings. Changes in temperature, pH, or salt concentration can affect their shape and function. If things stray too far from the enzyme's comfort zone, it may denature, lose its shape, and stop working. This is why fevers can be dangerous and why the body works so hard to maintain homeostasis. Life's chemistry is balanced on a knife edge, and enzymes are at the very center. Outside biology, catalysts play major roles in energy and manufacturing. In the Haber Bosch processor, which produces ammonia from nitrogen and hydrogen, an iron catalyst makes the reaction practical at industrial scales. Without it, we couldn't produce enough fertilizer to feed billions. In fact, it's said that half the nitrogen in your body was fixed from the air by this process, made possible by a humble metal catalyst. Catalysts are also used to make plastics, pharmaceuticals, fuels, and countless other products. Zeolites, microporous minerals, refined petroleum, sorting and rearranging hydrocarbons with precision. Transition metals like palladium and rhodium are used in fine chemical synthesis, where even small improvements can mean big savings. In green chemistry, catalysts are essential for making processes more sustainable, lowering energy, reducing waste, and enabling reactions under milder conditions. Some catalysts are inspired by nature. Biomimetic catalysts are synthetic compounds designed to mimic enzymes. They may not have the complexity of living proteins, but they offer similar specificity and efficiency. The field is growing quickly, blending biology, chemistry, and engineering in ways that could transform medicine and materials science. Interestingly, not all catalysts are on forever. Some are designed to deactivate at certain points, switchable catalysts that respond to triggers. These are being explored for drug delivery, where the catalyst activates only in the right environment or in smart materials that change properties with heat, light, or acidity. In chemistry classes, catalysts are sometimes overlooked, seen as supporting characters. But once you start noticing them, you realize they're everywhere. They enable change without changing themselves. They make the impossible routine. They accelerate progress without stealing the spotlight. They're chemistry's backstage crew, setting scenes, arranging props, and making sure the stars shine. That's the quiet power of a catalyst, enabling transformation with grace and subtlety, showing us that sometimes the greatest influence comes not from center stage, but from gently helping others do what they were meant to do. Now, let's turn to water, one of the strangest and most essential substances on Earth. It's everywhere, covering most of the planet, filling the air as vapor, flowing through your veins, and making up the bulk of every cell. Yet, for all its familiarity, water is quietly mysterious. It bends the rules, breaks expectations, and holds everything together with a chemistry that's easy to overlook. At first glance, water seems simple: 2 hydrogens and 1 oxygen, H on O. But this tiny V-shaped molecule is anything but ordinary. Water's strange and wonderful qualities all stem from its shape, its polarity, and the unique bonds it forms with its neighbors. These features give rise to a whole array of remarkable behaviors. Let's start with polarity. Water is a polar molecule, meaning it has a slightly positive end and a slightly negative end. That's because oxygen is more electronegative than hydrogen. It pulls the shared electrons closer, creating a partial negative charge on the oxygen side and a partial positive charge on the hydrogen side. The result is a tiny molecular magnet with a north and south pole. This uneven charge distribution is central to water's personality. Because of this polarity, water molecules attract each other through hydrogen bonding. Despite the name, hydrogen bonds aren't true chemical bonds. They're more like strong attractions between molecules. Still, they're powerful enough to hold water together in ways that defy expectations. Hydrogen bonding is why water has such a high boiling point. Most molecules of similar size, like methane or ammonia, are gases at room temperature. But water is a liquid, and not just any liquid. It has surface tension strong enough for insects to walk on, cohesion high enough to pull itself up plant stems, and a heat capacity so large it can absorb or release huge amounts of energy with only a small change in temperature. That's why coastal climates are milder. Water acts as nature's thermal cushion, evening out temperature swings and making life possible in a wider range of environments. Another oddity: water expands when it freezes. Most substances shrink as they solidify, but water's hydrogen bonds lock the molecules into an open hexagonal structure, taking up more space than the liquid state. That's why ice floats. It's less dense than water. If ice sank, lakes and oceans would freeze from the bottom up, trapping life and changing the planet's climate. Instead, ice forms an insulating layer on the surface, preserving liquid water below and allowing ecosystems to survive harsh winters. This simple quirk of molecular geometry has enormous consequences for life on Earth. Water's role as the universal solvent is another superpower. Its polar nature makes it excellent at dissolving other substances, especially ionic compounds and other polar molecules. Drop salt into water and the positive and negative ions are surrounded, separated, and pulled into solution. Water also dissolves sugars, gases, minerals, acids, and bases. This is why nutrients move through your bloodstream, why plants draw minerals from soil, and why water cleans so effectively. Without this dissolving power, transporting nutrients and removing toxins would be much harder. But water can't dissolve everything. Non-polar substances like oils and fats resist mixing with water, hence the saying, like dissolves like. Polar substances dissolve in polar solvents, non-polar in non-polar. That's why oil and vinegar separate in salad dressing, and why soap is so useful. It has one end that binds to grease and another to water, forming tiny droplets called micelles that can be rinsed away. On the microscopic scale, water's properties shape the entire world of biology. Inside your cells, water is the medium for thousands of chemical reactions. Enzymes, DNA, proteins, all fold and function in a watery environment. Water helps stabilize structures, shuttle ions, and even participate directly in some reactions. For proteins, water influences folding, and since shape determines function, water indirectly helps ensure that life's molecular machines run smoothly. Water is also the unsung hero of photosynthesis. Plants use sunlight to split water molecules, extracting electrons to help build sugars. The oxygen released, what you're breathing right now, comes directly from water in plants. Every breath you take is a quiet echo of this generosity. On a global scale, water sculpts landscapes, shapes weather, and even alters geology. It erodes mountains, carves canyons, and delivers sediment to river deltas. It moves heat around the globe through ocean currents and shapes weather patterns through its transitions between liquid, vapor, and ice. The water cycle is a seamless, never-ending loop linking oceans, clouds, rivers, glaciers, soil, and life. Chemically, water is stable but not inert. It can act as both an acid and a base, donating or accepting protons as needed. This makes it crucial in pH balance, buffering, and countless acid-base reactions in living things. Water is flexible, adaptable, and always involved. Despite its abundance, fresh water is rare. Less than 1% of Earth's total water is easily accessible. The rest is locked away in oceans, glaciers, or deep underground. Every glass you drink, every shower you take draws from this surprisingly small pool. In space, the search for water is central to the search for life. Wherever scientists find liquid water, on Europa, Enceladus, or Mars, they find hope for biology because water is so good at what it does: dissolving, stabilizing, transporting, and reacting. You too are mostly water, about 60% by weight as an adult, even more as an infant. Your blood, your brain, even your bones contain water. It cushions joints, regulates temperature, flushes waste, and delivers nutrients. And yet, water is easy to overlook until something runs dry. But once you notice it, its cleverness and importance become impossible to ignore. Water is a rule bender, a shape shifter, a quiet alchemist holding the secrets of chemistry in a single drop. Transparent, but never simple. For a molecule of just 3 atoms, water is full of wonder. Now let's turn to matter itself. At first glance, matter seems simple. It's what everything is made of: the chair you sit on, the air you breathe, the tea beside you. But beneath its familiar exterior, matter is always in motion, always transforming, always vibrating with energy, and sometimes pulling off surprising tricks. Understanding the states of matter is a peek behind the curtain of reality. It's less about rigid categories, more about a graceful dance of particles responding to temperature, pressure, and energy. We traditionally talk about 3 states: solid, liquid, and gas. Add plasma, and you have the classic quartet. But even these are just the start. There are exotic states like Bose, Einstein condensates, and superfluids under extreme conditions. Let's start with the familiar solids. In a solid, particles are arranged in a fixed, orderly structure. They can't roam freely, but they aren't completely still. Each atom or molecule vibrates in place, held tightly by strong forces, or, in metals and crystals, locked into rigid frameworks. When you touch a cold metal spoon or step onto a tiled floor in the morning, you're experiencing the stability of a tightly packed particle grid, a hallmark of solids. Whether it's a rock, a block of ice, or a wooden table, solids are resistant to change, at least until enough energy is added. Add heat, and the particles vibrate faster, stretching the bonds that hold them in place. At the melting point, these vibrations become strong enough to break the rigid structure. The particles don't fly apart, but instead slip past one another, and the solid becomes a liquid. Liquids are the social middle ground of matter. The particles remain close together, but they can move, flow, and slide around each other. A liquid takes the shape of its container but keeps a fixed volume. It doesn't expand to fill space like a gas. Water in a cup, a bowl, or your hands is still water. It changes shape, not size. Liquids are adaptable, with molecules constantly in motion, bumping and rearranging, yet still held together by intermolecular forces. Surface tension, viscosity, and capillary action are all expressions of these relationships. How closely particles stick, how easily they move, and how they cling to surfaces. Add even more heat, and the particles move faster. Eventually, they overcome the attractions that kept them together as a liquid. At the boiling point, they have enough energy to break free entirely and become a gas. Boiling isn't just bubbles at the surface. It's a full escape from the liquid state. Particles shoot into the air, spreading out to fill all available space, no longer tied down by structure or cohesion. Gases are the wild spirits of matter. The particles are fast, far apart, and mostly independent, expanding to fill any container. The air in a balloon presses against the rubber because gas particles are constantly bouncing off the walls. Open a window, and those particles drift out and mix with the broader atmosphere. Gases are compressible. You can squeeze them into smaller spaces, as in scuba tanks or bicycle tires, because the distance between particles is much greater than in solids or liquids. If you keep adding energy, cranking up the temperature far beyond boiling, gas particles gain so much energy that electrons are stripped away from their atoms. The result is plasma, a soup of charged particles, free electrons, and positive ions, all bouncing around energetically. Plasma might sound exotic, but it's the most common state of matter in the visible universe. Stars, including our Sun, are giant balls of plasma, so are neon signs, lightning bolts, and the auroras near the poles. Plasma behaves a bit like a gas, but its charged particles also respond to electric and magnetic fields in unique ways. Now let's reverse the direction. Remove energy, and the particles slow down. A gas cools into a liquid freezes into a solid. These reversals are just as fascinating as the forward changes. Condensation, gas to liquid, is how dew forms on grass and water beads on a cold glass. Freezing is when water molecules slow and lock into place, forming solid ice. Sometimes matter skips a step. Sublimation is when a solid turns directly into a gas without becoming a liquid first. Dry ice of frozen carbon dioxide does this, creating dramatic fog. Deposition is the reverse, when a gas becomes a solid directly, like frost forming on a window pane. All these transitions, melting, freezing, boiling, condensing, sublimating, and depositing, are phase changes. They don't change the substance itself, just its form. Ice, liquid water, and steam are all H on O. What differs is the energy of the molecules, their arrangement, and freedom of movement. Energy is the key. Temperature measures the average kinetic energy, how fast the particles move, and pressure influences how close they are forced together. These two factors determine the state of matter. Raised temperature and lower pressure, and substances are more likely to be gases. Lower temperature and raised pressure, and you get solids or liquids. Water's phase diagram, a map showing how its state changes under different conditions, has some quirks. For example, increasing pressure on ice can actually cause it to melt, not freeze harder. That's why ice skates work. The pressure under the blade lowers the melting point, creating a thin layer of water for smooth gliding. Understanding the states of matter isn't just about memorizing definitions. It's about seeing that matter is always in flux, always responding to its environment. At the particle level, everything is always moving. Even in solids, particles vibrate. In gases, they zoom. In liquids, they swirl and shift. Matter is never completely still. It's alive with energy, just moving at different speeds. There's something comforting about this. Your tea cools, molecules slow down. Energy relaxes into stillness. The air in your lungs expands and contracts with every breath. The ice in your drink melts, changing form, not identity. All around you, matter shifts quietly, following the timeless rules of thermodynamics, transitioning from one phase to another like scenes in a gentle, never-ending play. Change is constant, but also orderly. Nothing disappears. It just moves. Solid to liquid, liquid to gas, energy and energy out. A soft rhythm unfolding everywhere in the universe. Not every combination in chemistry ends with sparks or explosions. Sometimes things just mix, swirling together, settling into layers, dissolving or floating. No new molecules are formed, no bonds are broken or made, and the atoms remain exactly as they were. This is the chemistry of mixtures, solutions, and suspensions. Every bit as fascinating as the more dramatic, reactive kind. It's the everyday blending of substances that keeps your tea warm, your salad dressing separated, and your ocean salty. Mixtures are different from chemical reactions. In a reaction, atoms rearrange and new substances form. But in a mixture, the original components retain their identities. They're just sharing space for a while, sometimes closely, sometimes grudgingly. Take a cup of tea, steep a tea bag, and you're making a mixture. Water draws out colors, flavors, caffeine, and tannins from the leaves. But nothing new is formed at the molecular level. The water doesn't become tea. It simply carries dissolved molecules. With patience and the right tools, you could separate the water, caffeine, pigments, and oils back into their individual parts. That's a key hallmark of a mixture. You can separate it by physical means. Mixtures come in two main types. Homogeneous mixtures are uniform throughout. You can't see the different components. Salt water is a classic example. The dissolved ions disperse evenly, creating a clear, stable solution. Heterogeneous mixtures have visibly separate parts. Granola, vegetable soup, or vinaigrette are examples. The components don't blend uniformly, and if left to settle, the parts often separate into their own zones. A solution is a special kind of homogeneous mixture where one substance, the soluta, is completely dissolved in another, the solvent. In salt water, for example, salt is the solute, water is the solvent, and together they form a solution that's chemically uniform throughout. No matter where you sip from the glass, the salt concentration is the same. Solutions can be found in all states of matter. Air is a gaseous solution of nitrogen, oxygen, carbon dioxide, and trace gases. Alloys like brass or steel are solid solutions of metals. Most liquid solutions, from sports drinks to seawater, have water as the solvent, which is why water is called the universal solvent. Its polarity and small size let it surround and separate charged or polar molecules, making mixing easy. But not everything dissolves. Oil and water, for instance, famously resist blending. That's because oil is non-polar and water is polar. Water molecules prefer sticking to each other through hydrogen bonds and won't make room for non-polar oil molecules. The result is a heterogeneous mixture. Oil floats in droplets or forms a separate layer. This is a suspension, a mixture where particles are mixed into a fluid but not fully dissolved. These particles are large enough to scatter light and will eventually settle out. Muddy water, flour in water, and orange juice with pulp, all suspensions, cloudy, chunky, and clearly made of more than one phase. Unlike solutions, suspensions need stirring to stay uniform. Somewhere between solutions and suspensions are colloids, mixtures where tiny particles are evenly distributed but not dissolved. The particles are small enough that they don't settle out, but large enough to scatter light, a phenomenon called the Tyndall effect. Milk, mayonnaise, and fog are all colloids. They look uniform to the naked eye but behave differently from true solutions under a microscope. Understanding the differences between solutions, suspensions, and colloids isn't just academic. It affects how we cook, clean, manufacture, and medicate. Take salad dressing, it's an emulsion, a type of colloid where oil droplets are dispersed in vinegar or lemon juice. Left alone, oil and vinegar separate because they're immiscible. But shake it up with mustard or egg yolk, and those emulsifiers stabilize the droplets, making the mixture creamy and unified. In the kitchen, physical changes like mixing, grinding, melting, or freezing are part of everyday chemistry. They don't change the molecules themselves, just their arrangement. Shredding cheese, boiling pasta, or whipping cream are all physical processes. The chemical structure stays the same. Compare that to a chemical change like baking a cake. Mixing flour, sugar, eggs, and baking powder and then heating them causes chemical reactions. New compounds form. Carbon dioxide bubbles are released, proteins denature and recombine, sugars caramelize. The result is something entirely new, irreversible by just cooling or stirring it backwards. That's the difference. Chemical changes are usually irreversible, while physical changes often can be undone. Because substances in mixtures keep their properties, you can often separate them by physical means: filtration, evaporation, distillation, decanting, all techniques for separating mixtures. Salt can be reclaimed from salt water by evaporation. Sand can be filtered from water. Crude oil is separated into gasoline, diesel, and other products by fractional distillation sorted by boiling points. The ability to isolate and purify substances is at the heart of much of modern chemistry and industry. Even in nature, mixtures are everywhere. Blood is a complex suspension of cells, proteins, and nutrients in plasma. Soil is a heterogeneous mix of minerals, organic matter, water, and air. Seawater is a solution filled with salts, gases, and microscopic life. Clouds are colloids of water droplets in air. Life depends not just on chemical reactions, but also on how substances come together, interact, and sometimes remain separate. This brings us to a calming truth: not everything in chemistry needs to react. Sometimes, molecules simply coexist, mingling without losing their identity. Like friends at a party, they share space but dance to their own rhythms. Mixtures are about balance, blending and staying distinct, structure and motion, change and stability. Chemistry isn't always about dramatic transformations. Sometimes it's about gentle togetherness. So, whether you're watching salt dissolve in water, shaking a bottle of dressing, or sipping a cup of tea, you're witnessing the subtle, graceful side of chemistry, where particles meet, mingle, and drift apart without fanfare. It's chemistry with a light touch, no explosions, just the quiet beauty of things coming together and staying themselves. Some chemical reactions happen so quickly you barely notice. A match flares, fireworks burst, lightning creates new compounds in a split second. Others unfold slowly, like iron rusting or fossils forming over millennia, and some seem not to happen at all. But every chemical reaction has a rate, the reaction rate, which tells us how quickly reactants turn into products. It's measured by how fast something disappears a reactant or appears a product, like bubbles or color change. Reaction rates remind us that chemistry isn't just about what can happen, but about how willing molecules are to react and under what conditions. For example, leave milk out on a chilly day and it's fine for hours, but on a hot day it soars quickly. The molecules haven't changed their nature, but the rate at which bacteria break them down has increased, mostly because of temperature. temperature is one of the biggest influences on reaction speed. Heat is energy. When you raise the temperature, molecules move faster, collide more often, and with greater force, like dancers going from a slow waltz to a wild breakdance. More collisions mean more chances for bonds to break and new ones to form. But collisions only count if they have enough energy and the right orientation, like trying to high-five someone at the right angle and timing. Heating up the system means more collisions have the energy needed to climb the activation barrier, the energy hill a reaction must overcome. Concentration matters too. The more reactant particles in a space, the more often they collide, like a crowded subway leading to more accidental bumps. A beaker full of concentrated acid reacts faster than a diluted one, not because it's more potent, but because there are more particles present, increasing the odds of useful collisions. Surface area also plays a powerful role. If a reaction happens at the surface, like a solid reacting with a liquid or gas, increasing that surface area speeds things up. A sugar cube dissolves slowly in tea, but granulated sugar dissolves much faster. Crushing a sugar cube into powder makes it dissolve almost instantly. The same principle applies to many reactions. The more exposed surface area, the more contact between reactants, and the faster the chemistry unfolds. This is why powdered spices bloom in a curry and powdered explosives react more dramatically than chunks. The particles at the surface are the ones actually reacting. Grind or break things down, and reactions can shift from slow to spectacular. Still, not all reactions are easily sped up. Some are naturally slow because they involve very stable bonds or complex, multi-step rearrangements. In these cases, changes in temperature, concentration, or surface area may help, but sometimes they aren't enough. That's when catalysts step in. Catalysts don't change the starting materials or the final products. Instead, they offer a shortcut, a lower energy pathway for the reaction, like taking an escalator instead of climbing the stairs. You reach the same destination, but with less effort. Enzymes, the biological world's catalysts, excel at this. In your body, reactions that would take days or years in a test tube happen in seconds. Enzymes nudge molecules into place and stabilize tricky transition states, ensuring the chemistry of life runs smoothly and on schedule, from digesting breakfast to copying DNA. Light can also influence reaction rates. Sometimes, photons, particles of light, provide the energy needed to kickstart reaction. This is how photosynthesis begins. Sunlight hits chlorophyll, triggering electron movement. It's also how traditional photography works, with light changing the chemistry of silver compounds on film. In modern chemistry, understanding and controlling reaction rates is crucial for everything from industrial manufacturing to drug development. A reaction that's too slow may be impractical or unprofitable. One that's too fast might be dangerous or yield unwanted byproducts. Chemists spend time tweaking conditions, concentration, temperature, catalyst choice, to find the sweet spot where reactions are fast enough to be useful, but controlled enough to be safe. Even in cooking, you're controlling reaction rates. Browning meat triggers the Maillard reaction, a complex set of changes between amino acids and sugars that only happens quickly at high temperatures. Too hot, and you burn the food. Too cool, and it stays pale and bland. Refrigeration, meanwhile, slows reaction rates, keeping food fresh by making spoilage reactions crawl. Sometimes, reactions are so slow they seem not to happen at all, at least in our lifetimes. Glass is often incorrectly cited as a super slow liquid, but real examples do exist. Diamond turning into graphite, or ancient matter transforming into oil and gas. Reactions so sluggish they appear paused. On the other hand, some are fast and fleeting, like hydrogen and oxygen combining explosively to make water in a rocket engine, releasing energy in an instant. Understanding reaction rates means understanding time in chemistry. Every molecule is moving, colliding, and deciding whether to stay as it is or become something new. The speed of those changes depends on heat, pressure, size, shape, concentration, and sometimes a helpful catalyst. There's a quiet beauty in this. Every bubbling pot, rusted hinge, or ripening fruit is a slow bullet of molecules. Some race toward change, others linger in balance. Most move at a pace that matches the world around them. It's not about being fast or flashy. It's about timing. With the right conditions and patience, chemistry unfolds exactly as it should. Now, let's turn to biochemistry, the gentle, practical cousin of big, flashy chemistry. Biochemistry doesn't erupt into fireballs or fizz in dramatic swirls. Instead, it hums quietly in the background, keeping you alive moment by moment. It's chemistry in a cardigans. Efficient, endlessly detailed, and essential. Without biochemistry, there's no heartbeat, no memory, no breath, no thought. Every yawn, blink, and dream is powered by the tidy, tireless work of molecules behaving just right. At the heart of biochemistry are a few familiar stars: proteins, DNA, and ATP. These molecules are the main characters in every living cell, choreographed with exquisite precision. Proteins aren't just for muscles or nutrition, they're the workhorses of life. Built from long chains of amino acids, proteins fold into fantastically complex shapes. Each fold and twist is determined by the amino acid sequence, which is written in your DNA. The shape of a protein determines whether it acts as an enzyme, a structural support, a transporter, or a messenger. Enzymes, specialized proteins, are nature's catalysts, speeding up life's reactions. Without enzymes, digestion would take weeks. DNA polymerase, for example, copies your DNA every time a cell divides. Amylase in saliva starts breaking down starch as soon as you chew, working with uncanny precision like a lock and key. DNA deoxyribonucleic acid is the ultimate blueprint, storing instructions for building everything your body needs. Made from just 4 types of bases, adenine, thymine, cytosine, and guanine, arranged along a sugar-phosphate backbone, DNA's potential is nearly infinite. Every strand is a set of blueprints that runs the show from behind the scenes. ATP's adenosine triphosphate is the cell's rechargeable energy currency. When a cell needs to move, build, or send a signal, it breaks a phosphate bond in ATP, releasing energy and leaving ADP's adenosine diphosphate, which can be recharged for reuse. This efficient cycle happens billions of times per second in your body. All these reactions, protein folding, DNA copying, ATP cycling, make up metabolism, the web of interconnected reactions happening simultaneously to keep you alive. There's catabolism, breaking down molecules to release energy, and anabolism, building new molecules from smaller pieces. Destruction and creation go hand in hand, maintaining the system in perfect balance. You can think of metabolism as a city during rush hour, billions of processes, all organized and coordinated, each depending on the others, all happening just when and where they're needed. Imagine the city of your cell's molecules zooming along like cars, some heading for factories, enzymes, others stopping to refuel at gas stations, ATP, some transforming into buses or buildings, new compounds. Despite all this motion, there's little chaos. The city runs smoothly because of careful regulation. Cells don't let their reactions run wild. Many enzymes only work under certain conditions. Some need a helper molecule, a vitamin or metal ion, to function. Others are shut off when there's enough product, creating feedback loops that prevent waste or overheating. It's like a thermostat for your chemistry, stopping when the job is done. Not because the system is tired, but because it's efficient. Take glycolysis, the 10-step process that breaks down glucose for energy, making some ATP along the way. It's part of cellular respiration, the process by which your cells extract energy from food. If glucose were broken down all at once, it would release too much energy at once, potentially damaging the cell. Instead, glycolysis breaks it down gradually, storing energy in small, useful packets. Each step is carefully regulated and perfectly timed. The same principle applies to the citric acid cycle, the Krebs cycle, where molecules from glycolysis are further oxidized. Then, in the electron transport chain, high-energy electrons are passed from molecule to molecule like a bucket brigade, slowly releasing energy to pump protons across a membrane and generate ATP via chemiosmosis. It's chemistry performing a quiet miracle. One glucose molecule, fully broken down, can yield over 30 ATP molecules. But metabolism isn't just about energy. It handles building new cells, repairing damage, responding to hormones, and processing toxins. It manages everything from hunger and mood to muscle growth and immune defense. All of this depends on biochemistry reactions running smoothly, proteins folding correctly, energy flowing where it's needed. Sometimes things go wrong. A single misfolded protein can cause devastating diseases, as with prions, infectious proteins that can trigger neurological disorders. A missing or malfunctioning enzyme can lead to metabolic disorders, where certain compounds build up or fail to be broken down. These rare conditions reveal just how finely balanced life's chemistry is. Yet life adapts. Enzymes evolve, pathways reroute, and cells compensate in surprising ways. Biochemistry's resilience helps life thrive everywhere from hot springs to Antarctic ice. One of the most remarkable things about biochemistry is its universality. The same basic processes happen in every living thing, from bacteria to blue whales. DNA structure, ATP use, and protein coding are all shared. Life doesn't reinvent the wheel. For each new species, it refines and builds upon the same foundation. Biochemistry is the chemistry of life, but also the chemistry of stability and sustainability, looping, conserving, and adjusting. It's how life takes a handful of atoms and turns them into movement, thought, memory, and feeling, all without exploding, a quiet marvel. You're made of carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and a few trace elements. These atoms follow the same rules as those in rocks or the ocean, but in you, they assemble and react in ways that create order and purpose. Behind every breath, thought, and heartbeat is a molecular symphony, a whispering choreography of proteins, enzymes, and ATP, all working together to keep you alive. Biochemistry may be quiet, but it's the hum behind every smile and sigh, perhaps the most remarkable chemistry of all. Earth might seem solid and steady, a big rock in space, wrapped in clouds and oceans, but beneath the surface and above the clouds, our planet is a restless, dynamic chemical system. It breathes, cycles, and changes constantly. Mountains erode, seas shift, gases swirl, and deep below, molten rock churns. From the churning core to the icy poles, Earth is always reacting, literally. Chemistry keeps it all moving. Geochemistry is the study of Earth's chemical makeup and how elements interact over time. It explains why volcanoes erupt, why oceans are salty, and how ancient carbon in limestone ends up in the air or your soda. It's the chemistry of rocks, water, and gases, of slow drips and explosive bursts, minerals forming, breaking apart, and re-forming over eons. Start deep underground, where Earth's interior is a hotbed of chemical activity. The core is mostly iron and nickel, under immense pressure and heat. The mantle, a layer of molten and semi-molten rock, convects slowly, driving plate tectonics. The crust, a thin skin, floats on the restless mantle like cracked ceramic on bubbling stew. When these plates shift, crack, or dive under one another, chemistry gets dramatic. Volcanoes are one of the most striking displays of geochemistry. Magma, formed when rock melts deep in the earth, contains dissolved gases like water vapor, carbon dioxide, and sulfur dioxide. As it rises, pressure drops, and gases bubble out, like opening a shaken soda, but much hotter and more dangerous. Expanding gases drive explosive eruptions, hurling ash, rock, and lava skyward. But volcanoes do more than make a spectacle. They play a vital role in cycling elements through Earth's systems. Gases released contribute to the atmosphere. Minerals in lava break down and enrich soil. Even volcanic ash, once settled, can fertilize distant lands or alter the climate by reflecting sunlight. Once volcanic rocks cool at the surface, they begin a new chapter: weathering, the gradual breakdown of rocks by wind, water temperature, and chemical reactions. There's mechanical weathering, breaking rocks, physically and chemical weathering, which rewrites the molecular story. Chemical weathering happens when water, oxygen, carbon dioxide, or acids interact with minerals. For example, feldspar in granite reacts with slightly acidic rainwater, turning into clay minerals and releasing ions like calcium and potassium. These ions might travel to the sea, contributing to its saltiness or becoming part of seashells. Rainwater is naturally slightly acidic, as it absorbs carbon dioxide while falling, forming weak carbonic acid. This mild acid shapes landscapes, dissolving limestone to carve caves and sinkholes over time. It's not dramatic chemistry, it's chemistry with patience, transforming mountains to sediment drop by drop. The ions released during weathering don't just disappear. Many end up in the ocean, supporting marine life. Calcium and carbonate ions, for instance, combine to form calcium carbonate, the stuff of coral and shellfish skeletons. When these organisms die, their shells sink and accumulate, eventually forming limestone, a slow geological bank account, storing carbon for the future. And that leads us to the remarkable carbon cycle. The carbon cycle is one of the most important chemical cycles on Earth. Carbon moves through the atmosphere, oceans, rocks, soil, and all living things in a vast, interconnected loop. It takes different forms: carbon dioxide in the air, carbonate in water, organic molecules in living tissues, and fossil fuels deep underground. And in every place, it's constantly being transformed. Photosynthesis pulls carbon dioxide from the air, turning it into sugars inside plants. Animals eat those plants, use the carbon for energy, and then breathe it back out as carbon dioxide. When plants and animals die, decomposers break them down, releasing carbon back into the soil or atmosphere. Some of this carbon may end up buried and compressed over millions of years, eventually becoming coal, oil, or natural gas. When we burn these fossil fuels, the stored carbon is released back into the air as carbon dioxide. The same happens when forests are cleared, removing trees that would otherwise absorb soil. Volcanoes also release carbon stored deep in the mantle. Meanwhile, the weathering of rocks can trap atmospheric carbon in minerals. The oceans absorb carbon from the air and store it in surface waters, deep currents, and marine sediments. The result is a grand cycle, not a perfect loop, but a network with inputs, outputs, feedbacks, and delays, all of which have a profound effect on Earth's climate. Atmospheric chemistry is where the planet's balancing act is most delicate. The atmosphere isn't just air, it's a reactive blend of gases constantly undergoing chemical changes. Oxygen, nitrogen, carbon dioxide, water vapor, methane, ozone all interact to shape weather, climate, and the conditions for life. Take ozone as an example. In the upper atmosphere, ozone forms a protective shield that blocks harmful ultraviolet light from the sun, protecting life on Earth. But at ground level, ozone is a pollutant formed when sunlight reacts with car and factory emissions, contributing to smog and breathing problems. Methane is another important atmospheric gas. Molecule for molecule, it's a much stronger greenhouse gas than carbon dioxide, though less abundant. It's released by wetlands, termites, cows, and fossil fuel extraction. Methane doesn't just sit in the air, it reacts, breaks down, and plays a major role in our changing climate. Water vapor, the most abundant greenhouse gas, is a key player in the water cycle, evaporating, condensing, and falling as precipitation. Clouds, which form from water vapor, influence climate by reflecting sunlight and trapping heat. Clouds are also tiny chemical reactors, where acids, salts, and pollutants can interact inside microdroplets. Even rain is chemistry in action, pure water flavored with whatever it collects on its journey through the sky. Through all of this, Earth acts less like a static ball of rock and more like a living system. Some scientists see Earth as a geochemical engine, a planet with feedback loops, equilibrium points, and self-regulating processes. It's not conscious, but the interactions are so complex, it almost seems alive. The composition of the atmosphere affects temperature, which affects weathering rates, which affect carbon cycling, and so on. Chemistry here as memory, cause and consequence. The Gaia hypothesis, as from the 1970s, proposed that life helps regulate Earth's environment, maintaining conditions suitable for more life. While not accepted in all its details, this idea inspired research into how living things and the planet's geology interact. And there's no doubt they dose soil, bacteria fix nitrogen, forests release oxygen, oceans buffer heat and carbon. Life and Earth continually shape each other. All of this leads to something beautiful. We're not separate from the planet's chemistry, we're part of it. Our breath, food, bones, and blood are all made from atoms recycled by Earth's cycles. The calcium in your teeth was once in a star, then traveled through rocks, plants, and maybe even ancient animals. The nitrogen in your DNA may have once been sparked by lightning. The carbon in your breath could become food for a tree. Every breeze, cloud, or crumbling mountain you see is chemistry unfolding in slow motion, a vast, quiet laboratory of elements in motion. But chemistry isn't limited to Earth. It unfolds in the silence of space, between the stars inside them, and across the cold stretches where barely anything stirs. Out there, gravity rules, light takes years to travel, and chemistry continues to shape galaxies, planets, and even the atoms inside you. It's slower and more cosmic, but the rules are the same. Particles move, collide, fuse, and transform in elegant, sometimes explosive harmony. The most dazzling laboratory of all, stars. These immense balls of plasma are powered by nuclear fusion, where lighter elements like hydrogen are crushed under immense pressure and heat to create heavier ones, like helium. This process releases tremendous energy as heat and light. But fusion is more than just an energy source, it's elemental alchemy. In small stars, hydrogen fuses into helium and stops there. But in bigger stars, fusion continues. Helium turns into carbon, carbon into oxygen, then neon, magnesium, silicon, and so on, building up layers inside the star like a cosmic onion. This continues until iron forms. Iron is a turning point. Fusing it consumes energy rather than releasing it. At that point, the star can't support its own weight, gravity wins, and the star collapses. In the most massive stars, this collapse triggers a supernova, one of the universe's most powerful explosions. For a brief moment, a single star can outshine an entire galaxy. In the heart of that explosion, elements heavier than iron, gold, uranium, platinum, and more, are forged and hurled into space, seeding the cosmos with the ingredients for planets, moons, and life. It's not just poetry to say we're made of stardust, it's chemical fact. The carbon in your muscles, the oxygen in your lungs, the calcium in your bones. None of these elements were made on Earth. They were born in stars that lived and died long before the solar system formed. Every breath you take contains atoms with a billion-year history. Between the stars, space isn't empty. It's filled with vast clouds of gas and dust, nebulae. where stars are born. Atoms and molecules drift, collide, and sometimes stick together. Gravity can pull parts of a cloud inward to form protostars, the seeds of new suns. As they collapse, temperatures rise, fusion ignites, and a new star is born, surrounded by a spinning disk that may become planets. Within these interstellar clouds, chemistry happens in its own slow, cold way. Temperatures hover just above absolute zero, and pressure is incredibly low, yet molecules form. Hydrogen binds into HN, and you'll find water, ammonia, methane, carbon monoxide, even simple organic molecules like formaldehyde and acetylene. These often form on the surfaces of tiny dust grains, acting as miniature laboratories in space. Astonishingly, astronomers have detected over 200 different molecules in space, including some that are prebiotic, containing the building blocks of life itself. Amino acids, alcohols, and even sugar-like molecules have been discovered drifting in the distant clouds of space, suggesting that the basic building blocks of life might be common throughout the galaxy. These molecules can persist for millions of years, sometimes joining up with collapsing clouds that form new solar systems, carrying the seeds of chemical complexity into the next generation of stars and planets. As stars age and shed their outer layers, they release heavy elements back into space, enriching the interstellar medium. This cosmic recycling, from stars to clouds and back again, is how the universe becomes ever more chemically diverse. In the early universe, right after the Big Bang, there were only a few simple elements: hydrogen, helium, and a trace of lithium. Everything else, carbon, oxygen, iron, gold, was built later in stars, scattered by supernova explosions, and gathered up again into new forms. Closer to home, planetary atmospheres reveal another side of cosmic chemistry, shaped by sunlight, magnetic fields, and sometimes life. Earth's atmosphere is unique in the solar system, rich in oxygen and driven by an active carbon cycle. But every planet has its own chemical story. Venus has a thick carbon dioxide atmosphere, dense clouds of sulfuric acid, and surface temperatures hot enough to melt lead, thanks to a runaway greenhouse effect. Mars also has a Care atmosphere, but it's thin and cold, with dust storm and occasional traces of methane that intrigue scientists. Could it be geological or even biological? The gas giants Jupiter, Saturn, Uranus, Neptune are dominated by hydrogen and helium, with swirling clouds of ammonia, methane, and water. Lightning and powerful storms trigger high-energy chemical reactions. On Titan, Saturn's largest moon, the atmosphere is rich in nitrogen and methane, and the surface hosts lakes of liquid hydrocarbons. It's cold, alien, but chemically fascinating, a place where new kinds of chemistry might still be happening. Even comets, icy wanderers of the solar system, are more than just dirty snowballs. As they approach the sun, their surfaces vaporize, releasing water, carbon dioxide, ammonia, and organic compounds. These outgassing events give scientists a glimpse in the chemistry of the early solar system, preserved in these frozen time capsules. In the realm of exoplanets, planets orbiting other stars, chemistry has become a tool for discovery. By analyzing the light that passes through a planet's atmosphere as it transits its star, astronomers can detect chemical fingerprints. Absorption lines reveal the presence of water vapor, carbon dioxide, or even oxygen. As our instruments improve, we might one day spot the signatures of life on distant worlds, not by seeing creatures, but by noticing the gases and molecules their activities leave behind. All this reminds us that chemistry isn't confined to labs or to life on Earth. It is the language of the universe. Atoms come together, break apart, and reassemble, shaped by gravity, fusion, and time. Sometimes in all that vastness, atoms become conscious, able to wonder about their own origins. You're not separate from this story. You are a chapter in it. The iron in your blood, the calcium in your bones, the oxygen in your breath, all were forged in stars, drifted through space, and were woven into a living being. The chemistry that built you also built galaxies, moons, and nebulae. You are a collection of atoms that learn to think, feel, and marvel at its own beginnings. In the end, the cosmos isn't just out there, it's inside you as well. Every time you look at the night sky, you're seeing a reflection of yourself scattered among the stars. Whether it's hydrogen fusing in a distant sun or a molecule forming on a dust grain in a cold nebula, it's all chemistry, quiet, elegant, and universal. Even in the quietest moments, chemistry is never still. A cold cup of tea, a deep breath in the dark, the gentle creak of wood in a settling room. Beneath it all, atoms are in motion. Molecules shift, electrons dance, and forces balance. It's a rhythm too small to see, too constant to hear, but always there. Every moment, everything, every part of you is held together and changed by the slow, steady and sometimes spectacular poetry of chemistry. Over these chapters, we've explored the vast and varied world of matter, from the tiniest atom to the shining stars, from rust on a garden gate to the reactions inside your cells. Chemistry can be fast, explosive, and bright, but it can also be calm and patient, weathering stone, dissolving sugar, folding proteins with exquisite precision. We began with atoms, tiny building blocks, always in motion. We followed electrons as they lapped and rearranged, giving rise to endless chemical structures. We explored how bonds form, how energy drives reactions, how heat pressure, and even catalysts can nudge molecules to react. We met acids and bases, watched temperature and pressure shape the states of matter, and discovered the gentle hum of equilibrium. We saw chemistry move slowly and quickly, traced the drama of carbon and the elegance of organic molecules, and watched electrons travel in redox reactions, connecting batteries, metabolism, and rust. We met catalysts, the backstage helpers, and unpacked the secrets of water, perhaps the strangest and most life-enabling substance of all. We moved through solids, liquids, gases, and plasmas, each revealing a different kind of particle motion. We learned about mixtures, solutions, and suspensions, and saw how not everything reacts. Sometimes things simply blend or float apart. In reaction rates, we saw how time, heat, and concentration all play their part. Then we stepped into biochemistry, where proteins, enzymes, DNA, and ATP power the machinery of life. Every heartbeat, thought, and blink is powered by molecules working quietly and confidently. We stepped beyond ourselves into the chemical cycles of Earth and the cosmos. Volcanoes, carbon cycles, stardust, and interstellar clouds, all obeying the same rules from the smallest cell to the biggest galaxy. In the end, chemistry connects everything. Matter is never dull or truly still. Even when something seems to rest in your hand, particles are moving, bonds are vibrating, electrons are shifting. Stillness is full of life. That's the comfort of chemistry. Change happens slowly and quietly, as often as it does with drama and speed. Rocks where the trees grow, cells divide, oceans absorb carbon, and reactions burn or balance. Some need energy, some release it, and some hover at the edge of equilibrium. Behind every action, no matter how small or ordinary, is a story, a narrative of atoms seeking stability, molecules finding lower energy, and systems searching for balance. Chemistry is not just about things, it's about tendencies, probabilities, and desires. The periodic table isn't just a list. It's a cast of characters, each with its own quirks, preferences, and bonding styles. Whether we're marveling at how soup lifts away grease, how a battery lights up a flashlight, or how stars transform hydrogen into gold, we're seeing chemistry at work. Chemistry isn't something apart from us. It is us. The chemistry of water is the chemistry of your blood. The chemistry of carbon is the chemistry of your thoughts. The chemistry of light is the chemistry of sight. So, as we reach end of this journey through the chemistry of almost everything, I hope you've felt a sense of wonder for what lies beneath the surface of the everyday. I hope this was interesting, but not so interesting it kept you from relaxing. And if you are still awake, perhaps you've discovered something new about the world, or about yourself. Before you drift off, if you're listening with your eyes closed, I'd love to know, where in the world are you tuning in from? What time is it there? Are you cozy in bed under soft blankets? Or curled up on the couch with a pet? Is it the hush of night outside your window, or the quiet hum of a distant city? Let me know in the comments. I love hearing where these chemistry explorations find you. And if you enjoyed this gentle dive, if you found it relaxing, intriguing, or quietly thought-provoking, please consider liking this video or subscribing to the channel. It helps me keep bringing you more content like this, and it lets me know these calm journeys through science are bringing a little more wonder into your world. Thank you so much for being here, and for joining me in this quiet celebration of how the universe works, one invisible reaction at a time. And remember, even when nothing seems to be happening, chemistry is always happening. The atoms are still dancing, the molecules are still mingling, and the world, even in perfect stillness, is beautifully, endlessly alive.